Carnegie de Washington, D.C. desde el 2004 al 2007. Actualmente es profesora en la Universidad Estatal de California en Northridge, donde ha estudiado sismología marina y dinámica de fluidos geofísicos durante 17 años. Y también es directora del programa GEMS, Geologic Experiences for Marginalized Students. Ese programa proporciona desarrollo comunitario, apoyo académico y de investigación para mejorar la diversidad en todos los niveles académicos y sociales y brindar una representación equitativa de estudiantes marginados y subrepresentados. Entonces, el día de hoy nos va a presentar resultados de su investigación realizada en el Pacífico para resolver la controversia de la anomalía litosférica de Isabella. Entonces, le dejo la palabra a la doctora Dayantin. Muchas gracias por haber aceptado la invitación y estar aquí con nosotros.
Gracias, Lucia, por la invitación. Mi hablo, mi español no bueno. So I will speak in English, por favor. Yes, okay. Okay. Hello. So I would like to give you some preliminary results from surface wave tomography, shown here. Using resolving a controversy in the Isabella lithospheric anomaly in Central California. This is work I have done with many master's thesis, undergraduate thesis at Cal State University Northridge, including Cristo Ramirez, who is here now. He's the newest member. He's a postdoc. He's going to complete this analysis in the next 2 years. These are all the people who have been involved in this project. Lenin Escobar, Sampath Ratnaika, Lexine Black, Cristo Ramirez, Caitlin, Marshall. This is me and Monica Kohler. And this is the CSUN GEMS program. Many students have participated in this from the geological experience for marginalized students. We involved in this program. We support them to advance into the scientific field. So what is the motivation for this project? One of the scientific questions is very similar to northern Mexico. How does subduction terminate when consuming a spreading center? So the East Pacific Rise used to be offshore and has moved slowly towards the subduction zone in the last 50 million years. Are slab fragments a normal feature of terminated continental margins, or is it unusual? How does convergence evolve as subducting plates become younger and shallower with time as the spreading center moves to the trench? Another question we will be able to answer is the difference between oceanic plates and continental plates. Are they lithospheres the same? Are they different? What is actually driving subduction? Those plates are different. Is it simply the crust? Is there anything more? Most of these studies in the California use many stations on land here, but do not incorporate oceanic slab fragments, oceanic OBSs. So this is not working too well. I guess I'll just keep trying, yeah? This is better on this side? I don't know. It's okay. So we're trying to include ocean bottom seismometers in the lower half of the figure to improve coverage in the oceanic plate. Did I do something? So the study area in the north is the Sierra Nevada mountain range, the Great Valley. This is the San Andreas Fault. Gracias. Okay. Is it just me? Nothing. And the San Andreas Fault. So the area we're studying is just north of our stations, but it's on the edge of our experiment. We were not planning to study this area, but we have imaged this structure in the northern edge of our study region. So the Isabella anomaly is this blue anomaly. It's IA, is Isabella anomaly. It's about 7% higher than the surrounding region. Sí. Muchas gracias. Muy bien. Okay. So, okay, that's good. That's good. So this high velocity anomaly, okay, shown here, it was first discovered in 1980 by Susan Reikis as a PhD thesis from Caltech. So there are two hypotheses to explain this single anomaly. One is called continental delamination, where the continental plate is hypothesized to delaminate underneath the Sierra Nevadas. There's a hinge, and the rollback goes from the east to the west. This was observed in xenoliths by Dukia and Salibi 1996, where they observed a mafic crust extending to 70 kilometers depth beneath the Sierra Nevadas with garnet, eclogite, which was more dense than mantle peridotite. In 2005, Farmer et al. Also showed potassium metasomatism and low epsilon neodymium, suggesting continental delamination. But on the eastern side of the Sierras, they observe no lower crust is missing. It's only about at 35 to 40 kilometers, they observe peridotites and Harzbergites. They suggest that a asthenosphere is close to the crust and that there has been a delamination event. And about the same time in 1996, McLaughlin suggested that there's an oceanic slab fragment in this region at the same latitude near the coast in San Francisco. So in this case, age progressive volcanism that gets younger as you go north, and these hydrothermal veins that are offset and basins that are opening were suggested to be formed by a slab window. So the Farallon plate broke. There's a fragment here, and it caused a asthenospheric upwelling that would cause these features that are observed. And then in 2013, Wang et al. Showed this high velocity anomaly stops at 100 kilometers, and they suggested it originates offshore, west of the Great Valley, and is a Farallon fragment. It's an oceanic plate, and it's broken here. But there's not very good coverage offshore. The coastline ends here. There's no seismometers on the ocean side. Another feature observed by Yang and Forsyth in 2006 shows the Great Valley from A to A prime. This is at 36, 37 degrees latitude. High velocity anomaly dipping down towards the Sierra Nevada inland. But here they used land stations and some instruments in the Channel Islands, but 36 is here. There's very few instruments and nothing offshore. Okay, so we're going to look at our analysis using this deployment from 2010. I'm going to try to show you the video. Just to give you a geologic background of this region. This is from G plates. This is created by Cristo. Thank you very much. Ramirez, showing the East Pacific rise offshore, separated by the Farallon plate in gray and the Pacific plate in blue. And you can see the spreading center is offset. This is the spreading center. This is the spreading center. It's a long transform. It gets longer as the East Pacific rise approaches the spreading center. And then can you pause it here? Can you pause? And in this region at 23 million years, the East Pacific rise intersects with the subduction zone. Mexico is still intact. California is still intact, but now the San Andreas starts to form. And this triple junction between the North America, Pacific, and the Vancouver plate starts to move northward. Okay, thank you. Continue. Yeah. And now you can see that the Pacific plate sutures with this section of the continental plate in Southern California. It starts to move north. And you will also notice that Baja is doing the same thing about this time, 10 to 12 million years ago. And then can you stop it now? Okay, just hold for a minute. So now you can see that this is where the Isabella anomaly is. This is the Sierra Nevada range. This is the Great Valley. This is the region of our study. This is Point Conception, Long Beach. And now this is today. You can see Baja has also moved north. And offshore, we can see, I don't know if you can see on the seafloor, this square feature, seafloor volcanism, which is the edge of the Morro and Monterey fracture zone. Okay. So, this is just a repeat of that, showing the East Pacific rise reaching the trench. And in this region, Wang et al. Showed that volcanism also is age progressive, 20 million years on the coastline. It becomes younger into Nevada, which is attributed to subduction being older. When the East Pacific rise was further away, there's an older seafloor plate that has a very steep dip and an arc volcanism. And as the East Pacific rise gets closer to the trench, it's a younger seafloor. It's hotter, hasn't cooled, so it will have a shallower dip angle, and the arc will move to get to that location that's 110 kilometers deep. And the arc volcanism moves steadily towards the east. So the seafloor magnetic anomalies offshore are very interesting. In the farther to the west, it's very standard. You have long north-south magnetic anomalies and east-west fracture zones, what you expect in the seafloor. And in this region, which is about 36, 37 latitude, you can see the Monterey fracture zones are not east-west. They are northwest, southeast, and the magnetic anomalies are northeast, southwest. So the spreading direction has changed at this time, about anomaly 7 or 8. Also, the magnetic anomalies near the Patna escarpment have all been are all not uniform. They're irregular. They're more oriented north-south. Even down here by Baja, the magnetic anomalies are a little bit northwest, southeast, but they are not what there should be when they were formed offshore, which is uniform and north-south. We don't know the depth extent of these magnetic anomalies, if these are deep structures, crustal structures, or lithospheric structures. This is our project offshore, in 2010. This is Lenin Escobar. We did work at night, during the day, 24 hours. These ships are very expensive. We run 24 hours a day with a 24-hour crew. This is Cristo Ramirez on a different cruise, but it's the same. He's deploying a seismometer off the ship. I think that was the Melville, maybe. And then this was our deployment. We deployed 34 ocean seismometers, 24 broadband, 10 short period, and we also have DPGs that were very helpful. Many students, we had 20 students involved, plus 3 professors and PIs. These cruises are a nice way to get students involved into geophysics. So we recorded 80 earthquakes during a 12-month period with a very nice azimuthal distribution with a little bit of a gap in the northeast, but very large also. These are only from 5.8 up. We also recorded the Honshu earthquake with this data set and measured the tsunami traveling from the west coast, the west side of our array towards the east side, and there's a couple of papers on that. This is our array. This is the California coastline, and these lines are ray paths of surface waves which travel on the surface. So this large surface wave comes in from all these azimuths to all the stations. So where we have good crossing ray paths, we have very good coverage. So we have coverage outside of, I'll go to this side a little bit, outside of the research area. So not only do the stations record, but we can also get crossing ray paths outside the array, which allows us to consider the anomaly we're observing just north of the study area. So we're looking at Rayleigh waves. This is the largest wave on the seismogram. That's the P and the S, which is very helpful in ocean bottom data because the water waves add a lot of noise, and we can usually see the Rayleigh wave very clearly on the vertical component. We will be adding love wave data to this data set. Cristo Ramirez specializes in love wave data, but that uses horizontal components. So there's a lot more noise. It's more difficult to see, but he likes a challenge. So we also did some station corrections. Quite a few. We did amplitude corrections between the OBS and the land stations. We account for velocity variations in the water, the sediment, crustal thickness, fossil layers, lithospheric thickness, all as a function of age. And we look at different regions, which I'll show you shortly. And we look at periods ranging from 16 to 78 seconds. So this is one seismogram. This is the Rayleigh wave. If we filter it at 16 seconds, it looks very different than at 78 seconds. And each of these features senses a different depth in the earth. So one seismogram, because of these dispersive effects of Rayleigh waves, can give us velocity structure in the earth. It's usually a little bit better than depth resolution of body waves. So this is surface wave structure. So if we filter at 25 seconds, the peak depth of sensitivity is roughly 4/3 the period. So at 25 seconds, the sensitivity is around 33 kilometers, and this kernel is plus or minus 10 kilometers. So it's a depth slice, not an infinitely thin layer. But at 50 seconds, the sensitivity kernel, the peak sensitivity is about 67 seconds, but the kernel is deeper with a thicker slice, about plus or minus 25 kilometers. So as you get deeper, we have depth sensitivity, but the thickness of the layer becomes thicker because of the longer period and the longer wavelengths. There's also overlapping sensitivity between periods, so it's important to look at neighboring periods together, which should sample similar structure. So this is our inversion technique. So we consider teleseismic earthquake events, which are far from our station. They're very far, 30 to 120 kilometers. By the time they arrive at our area of interest, we approximate that incoming Rayleigh wave as a plane wave, but we know it can encounter perturbations in the wave field, such as continental margins, seamounts, oceanic plateaus, subducting plates, things that are non-uniform compared to a horizontally layered Earth. And so we allow for perturbations in the wave field by approximating the plane wave as two interfering plane waves, each with an individual amplitude, phase, and direction. And the velocity field is uniform but we also consider anisotropy, which adds two more terms to the model parameters. And then the inversion solves for the best fitting velocity when we do a least squares fit between the observed phase and amplitude at each station and the predicted phase and amplitude by this two plane wave model approximation. Okay, and we also consider finite frequency analysis in this inversion, which I can explain if you have questions. Okay, so this is the California coastline. These brown triangles are the stations, and these are different regions that we are solving for velocity. First, we solve uniform in the ocean, uniform on land. Then we use that in a multi-stage inversion to break up the regions by geologic structures on the surface. For example, the San Andreas Fault. We solve for the region east and north of the San Andreas and Garlock faults, also north of the Murray fracture zone, which has different velocities than the region south of the Murray fracture zone. We consider the outer borderland as a separate region from the inner borderland. And then notice the Murray fracture zone is right in here with these northwest, southeast fracture zones. Okay, so we do a multi-stage inversion. We solve for first a uniform velocity inversion in the land and the ocean, and then we do some amplitude corrections because we have such great azimuthal distribution. We can solve for amplitude corrections to all the stations. Some of those are the land stations as well. And then we can solve for two regions, use the output as input to the next inversion for 5 different regions. Use that as output for input into the shear wave velocity inversion. So I'm going to show you that here. Our first result for phase velocities, this is just for the oceanic seafloor in dark blue and land in yellow, is significantly higher in the seafloor compared to land at all periods from 20 to 78 seconds. Velocities are 4% higher in the oceanic seafloor compared to the continental lithosphere. Velocities in the borderland are kind of in the middle at periods below 40 seconds. The borderland is higher significantly than land and lower periods than in the deep ocean. So the borderlands are something that is not oceanic lithosphere and not continental lithosphere. At longer periods, the borderlands and the land have roughly the same velocities within air. Seismic anisotropy, I'm just going to show you a few results. This is the strength of peak-to-peak anisotropy on the vertical component. This is period going from shallow depths to deeper depths. And then the bar shows the fast direction of anisotropy compared to north in a map, east. And then this is the Pacific plate motion direction, which is roughly west-northwest. So all the anisotropy results less than 40 seconds have the fast direction, all very consistent in this region on average. West-northwest, east-southeast, consistent with Pacific plate motion direction. At the longer period, the azimuth changes to a northwest-southeast direction at deeper depths above 40 seconds. This is in the region here, north of the Murray fracture zone, where the Morrow and the Monterey fracture zones are. And then north of the Garlock, up here, these blue squares, the azimuth is roughly northwest southeast, very consistent with the fracture zones, actually. It's a little more complicated because there's a middle layer that's east-west, and then the strength of anisotropy decreases in both cases, and then we go back to northwest-southeast. So this one's a little more complicated. And I just wanted to show you, this is the azimuth of the Monterey fracture zone, which is significantly more northwest-southeast compared to the Pacific plate motion. Okay, so then we do a shear wave inversion for shear wave velocities, which is something people are used to comparing between different studies. This was our starting model for Nishimura and Forsyth for 20 to 50 million year old seafloor. Our seafloor is 15 to 35 million years. This is AK-135, a global Earth model for reference. This was our starting model, and with the shear wave inversion, we can predict phase velocities for the starting model and compare those to observed phase velocities in a least square sense and solve for the best fit shear wave velocity, which would be something like this. And these were our shear wave. This is shear wave velocity versus depth. And these are our starting models for the different regions. And those starting models were derived from geologic observations, active source, ODP cores, where we obtained MOHO depths, crustal velocities for each of these regions. This is a very nice study by Zhu and Karamori, which shows the MOHO depths, which vary all over California. SCEC has a nice model as well. These were our starting phase velocities. And these are some of our shear wave velocity results. So these are compared to AK-135. It's a global model, which is the same in all the results. This is depth down to 300 kilometers. And this is shear wave velocity that's increasing with depth. And we can see in the deep ocean, up to 35 million years, there's a strong high velocity lithosphere that reaches about 4.4 kilometers per second. A very distinguished low velocity zone here, and then an increase to regular mantle that does not seem anomalous. We define the base of the lithosphere as the middle of the negative velocity gradient between the high velocity lithosphere and the steep low velocity anomaly at roughly 85 kilometers, plus or minus 20 kilometers. This is a middle age seafloor, 15 to 25 million years, which also shows a low velocity anomaly. the outer borderlands and the inner borderlands. And this is the fit that produced these shear wave velocity results. Okay. In the Central Valley, the velocities in the lithosphere are not as significant or strong. They're gradually increasing. There's a very slight low velocity anomaly. This is beneath the Sierra Nevadas. We do not see a strong lithospheric signature. This is about 4.4 kilometers per second with a very subtle low velocity zone. And then we use those to solve for two-dimensional shear wave velocity variations on a map. So this is longitude versus latitude. These are velocities on a scale from 3.8 to 4.8 kilometers per second. And this here is the coastline, California coastline down here into Mexico. These are the Channel Islands. This is the San Andreas Fault, Garlock Fault, and this is the Murray Fracture Zone. And so our major observations are this strong high velocity anomaly offshore the coastline that seems to cross onto the continental margin at 80 to 90 kilometers depth. We also see a strong high velocity anomaly beneath the Sierra Nevada mountain range, consistent with previous body wave tomography results. And we also see a strong high velocity anomaly in the outer borderland that as you go deeper moves to the east and indicates a structure that is dipping. This is a steep dip compared to the Monterey Plate, which now moves inland also at 80 kilometers, but you can see this long structure looks like more of a shallow dip. And the anomaly beneath the Sierra Nevadas starts to become weaker at 100 kilometers depth. We also noticed the high velocities at the oldest age are 6% higher than velocities in the youngest age. So we're trying to compare this to just simple oceanic plate variations as a function of age. At 100 to 110 kilometers depth, the anomaly beneath the Sierra Nevadas mostly disappears. So it looks like that lithosphere underneath the Sierra Nevada is indeed gone by 100 kilometers, but the Monterey fragment, the Monterey anomaly is still here at 110 kilometers, but now has moved inland, is no longer offshore. And the strongest feature at this depth is a high velocity anomaly in the outer borderland that indicates a slab fragment exists in the borderland area. And so the Sierra Nevadas is in this area, and the Monterey fragment we see is over here near this Monterey fragment fracture zone. So our basic observations are that phase velocities in the seafloor are 4% faster at 25 to 35 million years, which is older seafloor compared to 15 to 20 million years, which is younger seafloor. The low velocity zone is stronger in the oceans compared to continents, and the high velocities in the seafloor are significantly higher than on land, and we suggest this is due to obvious differences we know in lithospheric formation in the oceans, which is a melting product at the spreading center where the basaltic crust in the peridotite lithosphere forms, moves away from the spreading ridge, cools with time, sinks into the deep ocean, creates the deep ocean basins, compared to continental lithosphere, which is formed by subduction zone, melting in the continental, in the wedge, and hydration of the continental lithosphere. So perhaps we're looking at hydrated peridotite lithosphere versus somewhat dehydrated peridotite lithosphere in oceanic versus continental regions. We also notice that the borderlands here in the white squares is significantly higher below 40 seconds, and this suggests there's some kind of underplating, thicker plate, something that Catalina schist obviously could be a factor in the borderlands area. So previous studies by Reeves et al. Did S to P converted phases where they can resolve reflected phases like MOHO locations, lithosphere, asthenosphere boundaries. In this case is the LAB, which is the base of the lithosphere. And they show that the base of the lithosphere indicates that there is a underplated oceanic fragment. This is consistent with our observation of two high velocity peaks. I had a poor undergrad try to take this out of the data using 1,000 starting models and different shear wave velocity inversions, and she could not remove this. And she came to me and said, nothing's happening. And I said, oh, it must be real. So this two double peak suggests there's two lithospheric plates in the outer borderland here. This is one model shown by Reeves et al. Of an underplated Farallon fragment. And they also observed a MOHO depth here that is quite deep in the outer borderland at 20 to 35 kilometers, consistent with continental MOHO depths. And the inner borderland has been known from several studies to be about 10 to 20 kilometers depth MOHO. So it's thinner than continental lithosphere, but thicker than a basaltic lithosphere. So the inner borderland is sort of a different animal. But first, I would like to talk about this anomaly, which looks like it continues. It starts in the deep ocean, continues across the continent, under the continental plate, and is consistent with a Farallon. We're going to call it the Monterey fragment. It's a piece of the Farallon. It's probably broken. It doesn't seem to go forever. And it does indeed cross the continental margin. And so hypothesis 2, we would say, is correct. However, we also see a high velocity anomaly underneath the Sierra Nevada mountain range that does not extend any deeper than 100 kilometers, suggesting that there could be delamination underneath the Sierras as well. And so we suggest these are two separate anomalies, and that hypothesis 1 is also correct, and that both of these hypotheses could be true, and these anomalies are separated as two distinct features that have been conflated in the literature. And finally, we observe this high velocity anomaly in the outer borderlands, which we believe is consistent with something. This is a structure that has continental lithosphere, continental MOHO depths, 28 kilometers in some cases, which suggests this is continental lithosphere. And if you look at some of those videos, some work that Luis Delgado showed this morning, the magnetic anomaly videos from Atwater, Robert Stern showed some recently, that McGeary and Wernicke, that this high velocity structure is continental fragment from northern Baja that fragmented about 12 million years ago, just before the opening of the Gulf of California, and has been moved upward as it was sutured to the Pacific plate and now exists offshore the coast, and we're considering calling this the Rosarita fragment. And we're looking at some information, some evidence of crustal extension and rifting on the west coast of Baja in northwest Baja today. So these are sort of my final results. This is a large project involving many people, and I thank you for your time.
¿Alguien quiere preguntar, comentar algo? ¿Sí? Ah, mira.
Thank you for that very nice explanation. I want to ask you now, there are so many things that resemble so much to the southern part of Mexico, where we really have the actual subduction occurring right now, especially on the tearings and also many other things that look like the lamination and many other things that we think that some of them may be also kind of controversial. Have you seen those on what can you say about our caucus plain beneath the North American, and what are more or less your thoughts about our actual subduction right now?
Yes, I think I'm learning more. One of the reasons I'm coming to the UGM conference is to understand more about the subduction differences. So I think what you see in the Cocos plate is what we have been describing at different times in the evolution of what occurred in the past in California. So what you're seeing is in present time is what probably occurred in the past. So the active subduction of the Cocos plate beneath southern Mexico, but that East Pacific rise is moving very close now, right, to the coastline. So at one point, I saw a talk, I think by is it Ramon? He got that big award to this time. So showing the quiescence of the seismicity at the boundary between North Baja and the Cocos plate. So that transition is changing. So, and then the opening of the Baja Peninsula, there's evidence. I've been reading some papers of a fragment offshore Baja also. But there's differences also. Obviously, in California, continental rifting has not opened completely. For some reason, it has opened in Baja, but it has not opened in California. I think that's a very interesting question to explain. Yeah, very interesting question.
Hi, thanks for the great talk. I was wondering if some of the differences between the velocities of the oceanic and continental lithosphere might be associated with the presence of the magmatic plumbing system in the continental lithosphere. Gracias.
Yes, should be the magnetic fluid system from arc melting. So when you have a subducting plate, you have arc melting. So it might be very interesting to compare the lithosphere in southern Mexico, for example, if that's where some people are doing their research, with the lithosphere in the Cocos plate. Both are supposed to be peridotite, but we're showing they will probably be different. So if you have a lot of magmatic flux, hydrothermal flux, hydrating that area, that definitely would lower seismic velocities in the continental lithosphere. And then magma fluxing in the lithosphere will create a different mineral composition, right, than in the oceanic lithosphere, which is simply melting from the spreading center. So you don't have that rehydrating, remelting, doesn't occur in the ocean. You just have one formation event from depleted morb. You're starting with depleted morb, however, so even in the spreading center. Yes, absolutely true. Very different.
Thank you very much for your talk. I am not a geologist, I'm an oceanographer, so, like this is, I get the point of what you're getting at, but my question is something very specific to the measurements that you make, because there's been a lot of conversation going on now with the idea that tomography can be used in both sort of disciplines, but I was wondering if your tomography, like your instruments that you're deploying in the ocean, are they bottom? I mean, do you put them in the bottom and from there do your tomography, or do you actually have them sort of like measuring the water column too?
Well, it's an interesting question. So the seismometers are very heavy, and we add iron plates to them. They're worth about $80,000 each, and we just throw them in the ocean.
All the way to the bottom.
And they sink to the bottom. And then we come back 12 months later to the exact latitude, longitude. We send a transponder signal. It burns one of the cables that's holding that plate. It drops the plate, and then the instrument has flotation, so it floats back to the surface. So for 12 months, it is on the seafloor. I would love to measure water wave currents.
I
I'm
thought it was
trying
like
to
when you said-
eliminate the water wave currents,
Exactly,
but
that's what I
obviously they're present in the seismic data.
Mhm.
And we have very high, I'm recording 40 samples per second. We could record more if it would help the oceanographers.
No, we require, like, I guess those frequencies are way too high for us in that sense, but yeah, there's well, anyway, there's a lot of people that are trying to talk about that, because what's noise for you is signal for us and vice versa.
Absolutely. And you're interested in the water at the bottom of the water column?
This is just a general conversation. I thought you had
Uh-huh.
like maybe, because in some cases when they're ship-based, then they're doing the tomography all the way from, like when they do explorations for oil or whatever, they're doing it from the surface all the way down. But I guess in your case, you really want to go deeper, so you're
Yeah.
yeah,
we're
but
interested-
like that being said, there's like signals on the floor that can be important, like even tides can be more accurately obtained that way, and that way we can get better tidal models. So yeah. So you
I've
don't
been
have
in
any
favor of
conversations
that
like
for a
that?
long time, because we
Okay.
also have no energy source at the bottom of the seafloor. So we have no solar energy. It's
Mm-mm.
pitch black. So we have to put giant lithium batteries down there, very expensive. And we bring them back. But if we could harness the water waves, to me, that would be an energy source of some kind, some kind of turbine. I don't know.
Okay.
I'm not an engineer, but it's just a wild idea. We do measure from the ship before we deploy. We measure. Natsumi was with that gun. She's actually measuring the water temperature and water column. We measure a lot of things in the water column, but it's just near the surface.
What do you want that for?
Just to know the temperature and the conditions that we're deploying in. It's just nice to know if it's uniform for all instruments or if it varies. But we do record and save that information, but most of the water column is not sampled. Yeah, maybe we can get you together with our OBS group and. Thank you.
Y va a seguir estando por aquí, entonces van a poder seguir hablando o discutiendo con ella. Muchísimas gracias. Nos vemos en la tarde. Muchas gracias.
If you have any questions and you want to ask in Spanish, Cristo Ramirez and I could answer together this afternoon. So thank you.
Thank you.